Welcome back to the Lesson BCE Explainer. Have you ever looked up at the night sky and wondered not just what those twinkling lights are, but how they got there and what's eventually going to happen to them? Well, today for Unit 5, we are going to explore exactly that. We'll uncover how stars are born from clouds of dust, how their initial mass dictates their dramatic life cycles, and most incredibly, how astronomers actually use their explosive deaths to measure the vastness of the universe itself. Here is our roadmap for today. First, classifying the stars. Then, the birth of a protostar. After that, we'll look at the solar mass path, followed by the high mass path. Then we get into the really wild stuff, neutron stars and black holes. And finally, measuring cosmic distances. Let's dive right in. Section 1. Classifying the stars. Before we can really understand how stars evolve, we need to know how we categorize them. And here's something that's kind of counterintuitive. On Earth, we're used to the red tap being hot and the blue tap being cold, right? Well, in space, it's the exact opposite. A star's color actually maps directly to its surface temperature. The coolest stars out there are red, burning at a surface temperature of around 3,000 Kelvin. As you move up the temperature scale through orange, yellow, and white, you eventually reach the absolute hottest stars. Those burn a brilliant blazing blue at a staggering 30,000 Kelvin. Section 2, birth of a protostar. Now, regardless of whether a star ends up as a cool red dwarf or a scorching blue giant, every single one of them shares the exact same origin story. It's like a cosmic factory. They all start hidden within a stellar nebula, which is basically a massive cloud of dust and gas floating out in space. Over time, gravity steps in and starts pulling all this material together. As the gas and dust condense, it gets hotter and hotter, forming what we call a protostar. Eventually, the pressure and temperature in the core becomes so intense that nuclear fusion actually ignites. Once that happens, the star stabilizes, officially entering its main sequence phase, which is where it'll spend the vast majority of its life. But here's where things get really interesting. Once a star hits that main sequence, its future splits into two completely distinct timelines. And which path it takes comes down to literally one single factor: its mass. It's either going to evolve as a star roughly the same size as our sun, or it's going to go down the path of a star that's much, much bigger. Section 3. The solar mass path. So let's talk about our own cosmic backyard. What does the future hold for a solar mass star like our sun? Well, as it finishes up its main sequence and runs low on fuel, it starts to swell up, expanding into this massive red giant. But it doesn't just stay like that forever. Eventually, it gently puffs off its outer layers into space. This beautifully expanding shell of glowing gas is called a planetary nebula. And these are absolutely crucial because they can actually provide the building blocks for entirely new planetary systems. What's left behind, right in the dead center, is a dense, incredibly hot core known as a white dwarf. Over billions of years, that white dwarf will just slowly cool down until it finally fades into a dark, cold, black dwarf. Section 4, the high mass path. Okay, so what about the heavyweights? For stars that have a much larger mass than our sun, the path leads to a way more dramatic fate. Instead of a regular red giant, the star bloats into a monstrous red supergiant. And because it's so incredibly huge, it burns through its remaining fuel at a furious pace. When that fuel finally runs out, there's no gentle shedding of layers. The star undergoes a catastrophic core collapse that rebounds into literally one of the most spectacular explosions in the universe, a supernova. If you're reviewing this for your exams, here is the absolute key takeaway. You've got to remember the difference between these two end stages. A solar mass star peacefully sheds its outer layers to form a planetary nebula, leaving behind a quiet white dwarf. But a high mass star? It goes out with unbelievable violence, ending in a supernova. Grasping this logical split is the whole secret to understanding stellar evolution. Section 5. Neutron stars and black holes. Now, the story of those high-mass stars doesn't just end with a giant flash of light. After the supernova explosion clears, that remaining core faces one of two extreme endpoints, again, depending entirely on the mass of the original star. It either collapses into a hyper-compressed, rapidly spinning object called a neutron star, or if there's enough mass, the gravity is so intense that it just continues to collapse completely inward on itself. And that leads us to one of the most fascinating objects in the cosmos, the black hole. If a star is among the absolute most massive in the universe, its core collapses entirely into a point where gravity is so overwhelmingly strong that it permanently warps the fabric of space-time. Nothing, not even light itself, can escape its boundary, which we call the event horizon. To really wrap your head around that level of density, think about this. For our sun to become a black hole, its entire mass would have to be crushed down into a sphere just 3 kilometers across. That's roughly the size of a small neighborhood. And these aren't just theoretical. Astronomers actually captured the first direct image of a supermassive black hole, named M87 star, back in 2019. Section 6. Measuring cosmic distances. So, now that we've followed these life cycles all the way to black holes, you might be asking yourself, why does this matter for understanding the rest of the universe? Well, it turns out astronomers use the predictable behaviors of these stars to build what's known as the cosmic distance ladder. The universe is just so unfathomably huge that we can't use a single measuring tape for everything. We have to apply different techniques for objects at vastly different distances, literally stepping our way up the ladder, rung by rung. For the closest rungs on the ladder, meaning the stars right next door in our own Milky Way, astronomers use a direct geometric method called parallax. But once we look out beyond our own galaxy, parallax completely breaks down. We're just too far away. So for distant galaxies, astronomers rely on something called standard candles. These are objects that have a known, predictable brightness. Cepheid variable stars are a classic example. But remember those massive supernova explosions we just talked about? Because specific types of supernova always explode with the exact same immense peak brightness, they act as the ultimate standard candles. They're literally lighthouses that let us measure distances across the deepest, darkest reaches of the cosmos. It is just wild to think that a star's violent destruction is exactly the tool we need to measure the cosmos. By mapping out where these supernovas go off, we are actively mapping the size, shape, and expansion of reality itself. Which leaves us with a pretty thrilling thought to wrap up on. If these stellar standard candles can tell us how big the universe is right now, what else might they reveal about the ultimate scale, and perhaps the ultimate future of our universe? Thank you so much for joining me on this Lesson BCE Explainer. Keep learning physics, and I'll see you in the next one.